Okay, so let's work on section 10.1. So we're entering a new chapter. We went through all our different hypothesis tests. We went through a plethora of them between chapter 8 and chapter 9. We had all these different hypothesis tests. We're going to continue with hypothesis tests. But let's remind ourselves of some things and learn some notation along the way. Sample mean. What do I use to represent that? X bar. Sample standard deviation? Proportion. Yeah, P chapeau, I like that. Parameters, mu, sigma, and P, which is annoying because P just gets used too much in this course. You got P values, probabilities, and we got another one coming up for us in this section. It's close. It's annoyingly close. So you may remember back earlier in this course we talked about linear correlation coefficients, right? So that was denoted by R. So that's going to be your sample linear correlation, or your sample statistic is an R. And it has an associated population parameter, which continues the trend of, now not quite the P, it's rho. So the Greek letter rho, which is a legitimate word in Words with Friends, if you ever play that game. It accepts your Greek letters, rho. So it's kind of like a script P. There's no little points here. And, look, I admit, it looks really close here. We're going to be testing the hypothesis as to whether or not rho is 0. So our null hypothesis is that rho is 0. What would be the alternative then to that? Rho is not 0. Let's understand the implications of rho equals 0 and rho not equal to 0 so that we can try and understand what's going on with this hypothesis test. It does look like a P, I understand. It's a rho. All right. Feel free to write a P on your test, and I'll feel free to mark it wrong.
Oh, you're so sad.
Yes?
Write like RHO instead?
If you want to write RHO, I'll accept that. Yeah. Just so you know, if you needed to do that on like Microsoft Word, you can. It's the symbol font. So if I change my font to symbol, then if I type in an R, it shows up as rho. Let me kind of increase the font size on that. There's your rho. So it looks like a P. I won't deny it. All right. I try to make mine look a little bit different. If I type in a P, it's going to come out as pi, I think. So pi, and then alpha, beta, gamma, delta, epsilon, phi, nu, tau, etc. So yeah, those are some of your Greek letters. It's just, occupational hazard. When you teach math, you learn a lot of Greek letters. Yeah, all right. So let's remind ourselves, though, of what's going on with our linear correlation. So what is it that makes something a perfect linear correlation? What's going on? There's two perfect linear correlations. There's one at -1 and one at +1. What's happening there that makes them a perfect linear correlation? Yeah, the data falls exactly on a straight line, perfectly on a straight line. Now, if you deviate from that a little bit, well, then you're going to be a little bit away from that perfect straight line. So you're at -0.94, or down here, +0.86. Now, both of these last two are 0 or near 0. Let's try and understand why. Remember, R is measuring the strength of the linear relationship. Is there much of a linear relationship up here with the third graph? No. And even though there is a relationship here in graph F, how come I'm getting a correlation of 0? Joyce, is there a question?
Oh, no.
Okay. So, well, I got a question for you then. How come I'm getting a correlation of 0?
I actually
Don't know? Some suggestions, Marvin?
It's quadratic, not linear.
Yeah, this is some other relationship other than linear. It's just not a line. And R measures the strength of a linear relationship, that is, how much of a line can be formed by your data. And there's, well, you know, as Marvin said, it appears to be like quadratic. It's just not a line. So that's why you're getting a 0 there.
No line.
It's just, yeah,
No line.
it's a circle, you know, a semicircle, but it's not a linear relationship. It's not a straight line. So if you do a hypothesis test here, rho equals 0 means there's no correlation. No correlation. Ow. Hate when that happens. Correlation. And rho is not equal to 0. That's where you do have a nice correlation. So there is a significant linear correlation. There is a significant linear correlation. So that's what you're getting when R is different than 0, or rho is different than 0. So if you're hoping for a relationship, then you're hoping to be able to reject H naught. Okay. Let's actually do some problems looking at some data. We'll start with example A on your handout. And I'll put that up in a second, just giving everyone a chance to copy this down. And let's put in a couple I's here. And there we go. All right, so let's take a look at this. Now it's funny, myself and one of my students looked at this lemons in cars. They thought of lemon as being a car that needs a lot of repairs, you know, which, yeah, I've had those. But they're actually talking about actual lemons, the type that you squeeze and get lemonade. So listed below are annual data for various years. The data are weights in metric tons of lemons imported from Mexico and U.S. car crash fatality rates per 100,000 based on, you know, some data from this journal. Is there significant evidence to conclude that there is a linear correlation between the weights of lemon imports from Mexico and U.S. car fatality rates? Well, you wouldn't think so, right? Is there any reason to believe that importing more lemons or importing less lemons is going to cause a change in our fatality rates? No, not really. Now, keep in mind that we live in a world that is swimming with data, and you are going to find these strange correlations, but that's going to be the subject of Monday's work, is trying to decide, is correlation mean causation? All right, so let's test this. So let's see, let me 5. So this is example A. H naught, HA. Is there a correlation between the weights from imports from Mexico and U.S. car fatality rates? Okay. So if there is a correlation, that would mean rho is not equal to 0. If there's not a correlation, that means rho equals 0. All right. And kind of looking at this of two minds. Testing whether or not there is a linear correlation, to me, suggests that our original claim would be that rho is not equal to 0. That's what I'm thinking. That's what I'm seeing at this. Like I said, for one of our problems in section 9.4, I'll try and be explicit about, you know, what we're testing, so you don't have to kind of guess about, you know, the original claim at all. Here, the original claim goes in the alternative hypothesis. We're going to test that at what value of alpha? Does it say? All right, so Madison suggests 0.05. Good. Let me swing it back over here. Derek, what's our third step, typically speaking, when we do these hypothesis tests? Yeah, input the data. And fortunately for us, you should have that data in the Google link that I shared with you. So it's over here. So example 10.1, example A, and kind of a small data set here. That's all right. Let's dump that into StatDisk anyways. If you need to get back to your data editor, just hit StatDisk Online. I'm going to clear out that old stuff and paste in the new stuff. Every now and then you'll get a phantom character of a space in your data set, and StatDisk will try and read it and it won't like it and it'll give you an error. So if you're getting some error and you're not really sure why, one of the things you can try would be to just clear out everything and start with some fresh data and make sure you don't have any blank spaces typed in there. Let's see, we got our data input. Let's work with step 4. What's our 4th step? What do I need for my 4th step? Say? P-value. I need a p-value. Where am I going to get a p-value? Analysis. Sounds good. Where should I go from analysis? Nick, any suggestions? Hypothesis testing would be a good guess, but I don't see anything that says... Oh, right underneath it is correlation and regression. So we'll go there. Our significance level is already dialed in. Let's set our column 1 and column 2. And bam, bless you. What's our p-value here? So p-value is 0.00992. Evan, what's that suggesting we should do with our null hypothesis?
Reject it.
Yeah, you're going to reject H naught. Our p-value is lower than this. Is that conclusion a surprise to us?
No.
Do you think there should be a correlation between lemon imports and car crashes? Well, that's what we're concluding, is that there is a linear relationship. Let's actually look at the data to see what's going on here. If you notice at the top here, amongst your sample editor and results, there's also another button called plot. Let's take a look at the plot. Does it look like these things are marching together? One goes down, the other one's going down? Yeah. Now, it could be that maybe we have better safety systems, better seat belts, airbags, that kind of thing. And at the same time, lemon imports from Mexico keep going down. Okay, that's fine. But that doesn't necessarily mean that one causes another. It just means that they're correlated. Correlation doesn't mean causation. So, I don't really think the amount of lemons we import from Mexico causes more or less car crashes. It just happens to correlate in this small data set. Let's actually write our conclusion in words. And back over to here. So where are we going to go? A, B, C, or D? Take a moment to decide that. Then we'll just take a look at it together. The original claim was that rho is not equal to 0. That is, there is a linear correlation. So A, B, C, or D? Stop. sample data. For how long?
Not very long.
Yeah, okay. So the part of Oz today is being played by Madison.
Yeah. Just her spirit is with us.
Oz is with us in spirit.
Yep.
Hello to Oz.
I know.
Which one do you think we should use here? Royale, what do you got?
See?
See? John? Thumbs up for that. Nick? Still deciding? All right. Christine, what are you thinking? A, B, C, G? Yeah. So the original claim does not contain the possibility of equality, so that brings us down this branch, and we rejected the null hypothesis, so that brings us over here. The sample data support the claim that. So let's start out by the sample data support the claim that. And now the stuff that follows that is going to come from the problem itself. There is a linear correlation between the weights of lemon imports from Mexico and U.S. car fatality rates. Is a linear correlation between the rates of, or the weights of lemon imports from Mexico and U.S. car fatality rates. You don't agree with that? Now keep in mind it just says correlation. Doesn't mean that one causes the other one. It's okay to be correlated. We're not saying that one causes the other one. So this is fine. All right. How are we looking on example A here? Okay? Thumbs up. Thank you, Carly. All right. Let's try another one. Example B. Yeah, Evan.
How are you supposed to answer the last question?
Oh.
Is it just no?
Yeah, this is something, like I said, we'll talk about more on Monday when we talk about correlation versus causation, but there's no reason to suggest that importing lemons causes car crashes. I just don't see any causal mechanism there.
Just no for now? Or is there a specific way we're supposed to answer that?
Let's see, it's a good question. You can say, no, there's no reason to think that one causes the other one. I mean, I do appreciate a complete sentence. No, there is no reason to suppose one causes the other. So I was talking to a chiropractor a while ago, and I've been aware of a correlation between people who get chiropractic adjustments and people who, those same people not getting sick as often. He goes, oh yeah, well there's an explanation for that. It's when you adjust your spine, it releases, or it helps develop more of a certain type of white blood cell that helps fight infections. So that you actually have a causal mechanism, one thing explains the other in terms of the results. So that's kind of the things that you're going to want to see when you start trying to move from correlation to causation. So yeah, good question. Thanks, Evan. Let's move down to example B here. And this one would be kind of nice, assuming that it's true. So what would be the advantage if there's a correlation between the overhead photograph that you take of a seal and look at the overall head width and its weight. What would be the advantage of being able to do this with a photograph? Be able to weigh them with a photograph? Yeah, not having to put them on a scale. Yeah, it'd be pretty nice. So if there is a nice correlation, then we can, make some of our observations a lot easier. So let's take a look at that. So it says, if the weights could be determined from overhead photographs, is there sufficient evidence to conclude that there is a linear relationship between overhead widths of seals from photographs and the weights of these seals? So, is there this correlation? Well, let's find out. Okay. So for myself, I kind of read this as saying test that there is a correlation. And if there is a correlation, assuming that there is a correlation, what's that saying about rho if there is a correlation? Equal 0 or not equal to 0? Not equal to 0 is really what that's asking. It's like, yeah, we think there is a correlation. Let's find out. Okay, so let's do that. So example B. Let's see, so H naught such that rho equals 0 versus HA, and who's a shout out? I think it was Nick. I think you suggested this, rho not equal 0. You wanted to actually write out rho. I'm fine with that. If not everyone's really good at making these Greek letters, that's fine. That's kind of a nice workaround, so I appreciate that. So that's your step 1. Step 2. Marvin, what do we got for step 2?
Alpha 0.05.
All right, alpha is 0.05. I don't think they actually gave us a value of alpha here at all, did they? 0.5 or 0.01. We'll go with 0.5. I mean, that's typical. I don't think we need to really be overzealous in going with a 0.01 level for this kind of data. Input the data. Did I hear a yawn? Oh, man. Wounded. Man. If I had feelings, they'd be hurt. If I had feelings, yeah. I'm a robot. If you look inside, I got a graphing calculator for a heart.
I believe it.
Yeah, I'm sure you do. All right, let's see. So example B here. Here's our data. Let's copy that and paste that into StatDisk. So click on the StatDisk icon in the upper left. Clear out the old stuff, paste in the new stuff. You can probably paste in right over it. I just don't like getting any of those weird characters stuck in my data. Analysis, correlation and regression. 0.05, 1 and 2. Do you expect a good correlation in this one? Probably. Now, a good correlation, do you expect it to be positive or negative? Do you think if the width goes up, the weight's going to go up? That makes sense, that they both increase at the same direction, so you have a positive correlation. If you look at the plot, certainly that's what the plot seems to be suggesting, is a positive correlation. Okay, looking good there. Let's go back to the results. Matt, what do I need from this page right here?
P-value.
P-value, good. So the P-value for us is 0.00391. The nice thing about giving the p-value in and amongst your results is people can decide for themselves some people test at the 5% significance level. Some people might say, you know what, I want to do my test at 0.01. And if you give them the p-value, they can make that decision for themselves. So it also lets you make your own decisions. So that's kind of nice to give people the p-value. What decision does that lead to? Carly?
You reject the
Good. We'll reject H naught. And let's see, step 6. Our original claim did not contain the possibility of equality, so I think that's going to correspond to a C from this chart. Did not contain the possibility of equality, and we rejected it. So the sample data support the claim that there's a linear correlation between overhead widths of seals from photographs and the weights of those seals. So the sample data support the claim that there is a correlation between overhead widths of seals from photographs. Let's go cheap. We're just going to write photos and the weights of the seals. Beautiful. Beautiful. All right. Let's see if I've got I think I got a link to a place where you can get some data, a website called CODAP, which is like Common Online something or other. Analysis of data. Can't remember what the P stands for. But it should be in the links in the announcements page. So just click that one, open it up, and it's going to take you to a page that says open a document or browse examples. So we're going to want to do this top one here. I'll wait a few seconds to make sure everyone's with me. Do you got that CODAP page open? Anyone need a few more seconds? Okay, a couple more seconds coming up. And if you're watching this later, then there's a QR code for the link. Ooh, pretty cool. Yeah, high tech for sure. All right, we all got this link open? Yeah, Matt, Joyce, Royale? Good. All right, click this first one here. It says open document or browse examples. And the example that we want to choose is the roller coaster example. So click that one, and then you want to open it. So yeah, we have taken a look at this before. We took kind of a quick peek a while ago. Open that one up. This describes your data set. So if you want to read that in more detail, you can. That's great. I'm going to get rid of it for now. Don't need it. Instead, I'm going to take and drag these two things over a little bit. This represents your data. It's data from like a gazillion different roller coasters here in the United States. It's got the coaster, the park, the top speed, the max height, the drop, the length, the duration in seconds, the type. Is it wooden? Is it steel? Is it sit down? The year it opened, the age, all kinds of things. So if you click one of these dots, it'll show you, oh, this one's Alpengeist. All right, so it's in Busch Gardens, etc. It tells you all about it. Here's what I want to do. This is going to be kind of the fun part. Let's drag some of the some of the variables over to the y-axis. Now, what's the fun thing about being on a roller coaster? Speed, right? You want to go fast. So, let's see. Up here in your data set, you should see a little variable that says top speed. Click on that and drag it down to your y-axis. So click, hold and drag your top speed and drag it down to the y-axis. Ooh, ah, that's kind of cool. Let's try that again. If you miss it the first time, you can get it the second time. You're going to click and drag. I'm going to drag that to my second one. So there you go. Those are the different top speeds. And if you're curious about one, you could click on it. For instance, there's one with a top speed of 120 miles an hour. That's your top thrill dragster down at Cedar Point. Woohoo! Yeah, that one's a blast. All right. Now, what do you think it is that could explain, how fast your coaster goes? Do you think that the year it opened, is that going to have much of a explanation? Might have a little bit of one, but I don't think it's going to be the big thing that really explains. You could drag year opened down to the y-axis. Is that much of a linear correlation? Doesn't look like it. Now, to actually figure out how much of a linear correlation there is, click the ruler right here next to your plot, and then, let's see, least squares line. And it doesn't give you the value of r, but it gives you the value of r squared. So one more time, you click the ruler. The ruler should be to the right of your graph along the vertical axis. Click the ruler, then click least squares regression line, least squares line. It's not giving me the value of r, but it is giving me the value of r squared. Now it looks like 0.138. Are you getting that, Matt? It's not showing up there for you? Click your graph. Actually, just click in the graph area someplace, and it should give you this little palette of options on the right-hand side. So if you click in the white area someplace, that should pop up. Then click the ruler, and then just measure center, measure spread, count. How come this is giving me something different here? Oh, you know what? That's because I haven't dragged over a variable for the x-axis yet. So let's do a better one. My guess is that the maximum height might be a better predictor of the speed here. So let's drag that one down. Does that look like there's more of a correlation there? Maximum height? Yeah, that's looking pretty good. Now when I click the ruler, one of the options I'll get is least squares regression line. I'm getting an r squared of 0.79. But if you remember, we don't want r squared, we want r. How are we going to go from r squared to r? What do you think we have to do? Take the square root. So let me just do that here. I'm sorry, this takes forever to open. All right, you know what? Oh, that was actually better than usual. So the square root of 0.79, one more time, square root of 0.79, that's going to be our r value. It should be about 0.9, I'm guessing, 0.888. That's pretty good. That's a really good value of r. That's pretty close to a straight line. How about the other one? Do you think we have a good value of r for our other data set here? Square root of 0.138. I'm thinking that's not going to be all that big. Square root of 0.138. 0.37. Not very good. No, not very good. So not a surprise. Now later we can play around with this a little bit more, and we're going to understand what the r squared represents when we cover section 10.2. But for now, it's just enough for us to see that, yeah, the value of R here looks like it's pretty good. Almost 0.89. So pretty good. All right, a couple more things to finish off before we're all set here. Let's flip things over. So again, there's a nice QR code if you wanted to scan this in to get to the Desmos link here. So this is another link that I gave you on our website. Desmos, but in a non-threatening way, right?
Non-threatening way, thank you.
All right. So let's get rid of this. So we've got two different data sets. This is how fast somebody runs a race. You know, the race, that's the distance, that's the time. Here it's distance in miles. So that's our X. And time in minutes, that's your Y. And you get this plot of the data that we have here in Desmos. So that's the black dots there. Let me just cover up the orange ones for a second here. What kind of a value of R do we think we're going to get here? Is that going to be close to -1, close to 0, close to 1? Close to 1. Yeah, looking like it's pretty close to 1. In fact, if you actually look at the output from this, here's your value of R right there, 0.9993. That's almost perfect. That's just a hair underneath perfect. So not a surprise there. But what if somebody says, you know what, hey, I'm from Canada. I don't understand miles. And you convert from distance in miles to distance in kilometers. So this is your X and this is your Y. So it's essentially the same Y values with different X values, but has changing these units, has that made a difference to our linear correlation coefficient?
No.
Let's take a look. Let's add that plot of data to our Desmos. Here it is in orange. What kind of value of R does that look like it's going to have? Kind of pretty much like the last one, right? And if you look at the value of R that you get there, it's exactly the same. So doing a linear change in the coordinates like we did didn't affect the correlation coefficient at all. Both of these are nice, almost perfect straight lines. Yeah, so they're both really, really good. So changing those things doesn't really make a big change to, or doesn't make any change to the linear correlation coefficient. Nice. So the answer here is no. Does changing the units affect the value? No, it didn't. It did not. Okay, let's move down to our last example, E. 20 different statistics students are randomly selected. For each of them, their body temperature in degrees Celsius is measured and their head circumference is measured. For this sample of paired data, what does R represent and what does rho represent? So they're asking you the difference between these two figures here. What's R representing? Somebody said it. Sample what? What's that sample statistic represent?
Linear correlation.
Yeah. The sample value of the linear correlation coefficient. What about rho? what's rho going to represent in contrast? Yeah, the value of the population how do I want to write this? Value of population parameter for the linear correlation coefficient. Almost done here. Almost done. And I want you to think about this for a second. Without doing any research calculations or anything, estimate the value of R. So if you collected this data, what kind of value of R are you going to get? So think about it for a second and then talk to a neighbor. All right. Let me just hear some values. I want to hear from you closer to -1, closer to 0, or closer to +1. So, Derek, start us out. Closer to -1, closer to 0, or closer to 1. What are you thinking?
Closer to 1.
Closer to 1. All right. Carly?
0.
Closer to 0. Nick?
Closer to 1.
Closer to 1. I appreciate the variety there, right? We got everything. So our three choices are closer to -1, 0, or 1. We need a deciding vote. All right, what do we got? Deciding votes?
0.
0. Matt?
0.
0. Is there any reason to suspect that you can predict, your body temperature based on your head circumference?
No, that'd be really cool though.
No, it'd be interesting, I guess. Maybe, sort of, not really, but whatever. But no, there doesn't seem to be any reason that your head circumference is going to predict that. Now, as far as which one of these statements go with below, there's one thing that I would get rid of right away. If I was taking a test and I saw something like this, I'd say, oh, let's get rid of this. Let's get rid of D. Why can I get rid of D right away? Yeah, it says R is a parameter. Well, R is not a parameter. R is a sample statistic. So we'll get rid of that. And up here in problem A, they explain R pretty good. They said R is a statistic that represents the value of the linear correlation coefficient computed from the paired sample data, and P is the parameter that represents the proportion of variation. Oh, wait, back up. The proportion of variation? No, that's not right. So, yeah, hasta la vista, baby. C, R is a statistic that represents the proportion of variation. Oh, stop there. It's not anything about the proportion of variation. That's getting close to the R squared that we'll study in section 10.2. How about this one? R is a statistic that represents the value of the linear correlation coefficient computed from the paired sample data, and rho is the parameter. All right, I like that. That represents the value of the linear correlation coefficient that would be computed by using all of the paired data. Remember, your parameters come from the entire population. So you'd have to have all the data, and that one's a winner. Nice. Nice. Anything else? See ya.